Today I'll be showing you how to do optimization using calculus. Optimization essentially means maximizing or minimizing a quantity to solve a problem. So for example, you could use optimization to find the maximum area you can enclose with 100 meters of fence, or maybe the ideal price to sell a product at to maximize profit. So on screen here we have an optimization problem which I'll go through to teach you the steps of optimization. So a farmer wants to construct a paddock using 200 meters of fencing. What dimensions would maximize the area? Alright, to do a problem like this, the first thing you want to do is figure out which quantities are involved. So we're working with the area of a paddock. So we're going to use the area. And we're also going to use the length and the width, because those are the dimensions that make up the area. And if you can, it's always good to draw a diagram. So let's do that. The paddock's just going to be a rectangle, and I'm going to let the width equal x and the length equal y. And then the next step is to write an equation for the quantity that you want to optimize. So we're optimizing area. So the equation would be that area equals x times y. Now this is where calculus comes in. So to find the maximum area, we can differentiate the equation for area. But to do that, we need area to be in terms of only one variable first. So let's try write it in terms of only x. So how can we represent y in terms of x? We can use a constraint that the total perimeter is going to be 200 meters. And if you think about it, the perimeter would also be 2x plus 2y. Because this here is also x and this here is also y. So if 200 equals 2x plus 2y, that means that 2y equals 200 minus 2x. And if you divide everything by 2, y equals 100 minus x. So now that we have y in terms of x, we can rewrite area as x times 100 minus x. And then you can turn that into 100x minus x squared. And now to find the maximum value of 100x minus x squared, you can differentiate it and set it to 0, because differentiation gives you the rate of change of the function, and if it's 0, that means that it's either a maximum or a minimum. So differentiating area gives 100 minus 2x. And now we need to set that to 0, so 100 minus 2x equals 0. Then we can add 2x to both sides. So 100 equals 2x. And then if we divide both sides by 2, we get that x equals 50. So x equals 50. We're almost done now, but we can't actually be sure if it's a maximum or a minimum yet. So to know if it's a maximum or minimum, we need to take the second derivative. If the second derivative is negative, it's at a maximum, and if it's positive, it's at a minimum. And you get the second derivative by just differentiating it again. So the second derivative of area would just be -2. And therefore it's a maximum because -2 is a negative number. So the area is maximized when x equals 50. And because the perimeter is 2x plus 2y, that means that y would also equal 50, because the total perimeter is 200. So the area is maximized when the paddock is 50 by 50 meters, and therefore has an area of 2,500 meters squared. There are tons of different optimization problems that you might encounter, but luckily they all essentially follow the same steps. So I'll just quickly recap those. So the first step is to identify relevant quantities and draw a diagram if it's applicable to the problem. Then you want to write an equation for the quantity being optimized. And step 3 is to rewrite the equation in terms of only one variable. So this step kind of depends on the problem, because sometimes there's only going to be one variable anyway, so you'll be able to skip this step, but sometimes there'll be multiple. Next you need to differentiate the equation, set it to 0, and solve it. Then step 5 is to check if the quantity's been maximized or minimized using the second derivative. And the final step is to use the known value to find any other variables. Alright, here's another question. An open top box will be made by cutting squares out of each corner of a 40 by 60 centimeter sheet of cardboard and folding the tabs up to form a box. What size square should be cut out to maximize the volume? And I've already included a diagram just to help you understand the question. Alright, first let's list the relevant quantities. So we have the volume, we have the 60 centimeter starting width, we have the 40 centimeter length, and let's say that the side lengths of the squares are x, so we also have x. Alright, next let's figure out an equation for volume. So volume is width times length times height, but we need to try to rewrite that in terms of only one variable. The width would be 60 minus 2x, because there's an x on both sides like this. That means that the length would be 40 minus 2x, and the height would just be x. Because if you visualize it in your head, when you fold it up, the height of the box is just going to be the same length as the side length that you cut out. So that means we can rewrite v as 60 minus 2x times 40 minus 2x times x. And if you expand the brackets, it becomes x times 4x squared minus 200x plus 2,400. And then if you expand that further, you can turn it into 4x to the power of 3 minus 200x squared plus 2,400x. Alright, now that we have an equation for volume in terms of only one variable, let's maximize it by differentiating it and setting it to 0. Alright, so differentiating the volume, we get 12x squared minus 400x plus 2,400. And then we can set it to 0, and we can solve for x using the quadratic formula. So x is going to equal negative b plus or minus root b squared minus 4ac over 2a. That's just the quadratic formula. So therefore x is going to equal negative 400 plus or minus root negative 400 squared minus 4 times 12 times 2,400 over 2 times 12. And plugging that into a calculator, we get that x is approximately equal to 25.49 centimeters or 7.85 centimeters. So now we have two values, but we don't know which one's a maximum. So let's take the second derivative of volume. That's just going to be 24x minus 400. So let's plug both values of x in. So first, if we plug in 25.49, we get 211.76. And that's a positive number, so therefore it's a minimum. Now if we plug in 7.85, so 24 times 7.85 minus 400, and that equals around negative 211.6. So because it's negative, that means that it's a maximum. So that means to maximize volume, the squares that you cut out should be 7.85 by 7.85 centimeters. Alright, here's one last question. A company needs to build a closed cylindrical can to hold 1 liter of liquid, which is 1000 centimeters cubed. The metal for the sides costs 2 cents per centimeter squared, and the metal for the top and bottom costs 5 cents per centimeter squared. What dimensions will minimize the total cost? Alright, first let's identify all the relevant quantities. So a volume of 1000 centimeters cubed is required. The price of the sides is $0.02 per centimeter squared. And the price of the top and the bottom is 0.05 per centimeter squared. Now I'll just quickly draw a diagram of the situation, even though it's not really 100% necessary, but just to help us visualize it. So it's a cylinder, like this, with a height h and radius r. The volume is 1000 centimeters cubed. The price of the sides is $0.02 per centimeter squared, and the cost of the top and the bottom is $0.05 per centimeter squared. So the cost of the cylinder is related to the surface area. The surface area of the sides of the cylinder is going to be 2 pi RH, and the surface area of the top and bottom together is 2 pi r squared. So using that, we can come up with an equation for the cost. So the cost is going to be 0.02 times surface area of the side of the cylinder, which is 2 pi RH, plus 0.05 times the surface area of the top and bottom, which is 2 pi r squared. So we're essentially just multiplying the surface areas by the costs that are given in the question. So now we have an equation for cost, but we need to try find a way to write it in terms of only one variable. So let's try write it in terms of r, and to do that we're going to need to find a way to represent h in terms of r. We can use a constraint given in the question, that volume is 1000 centimeters cubed, because the volume of a cylinder is given by pi r squared h. So that means that 1000 equals pi r squared h. So therefore h equals 1000 over pi r squared. So now we can rewrite the cost as 0.02 times 2 pi r, 1000 over pi r squared, plus 0.05 times 2 pi r squared. And now I'm just going to try to simplify this so we can get it in a form where it's easier to differentiate. So let's rewrite it as 0.02 times 2000 pi r over pi r squared, and then we can also cancel out the pi r, and then go plus 0.1 pi r squared. So let me just rewrite that as 0.02 times 2000 over r plus 0.1 pi r squared, and then that just equals 40 over r plus 0.1 pi r squared. And just to make it easier to differentiate, I'm going to rewrite the 40 over r as 40 times r to the power of negative 1, because those are the same. Then I'm just going to do the 0.1 pi r squared again. And now to minimize the cost, we can differentiate it. So differentiating cost, we get negative 40 r to the power of negative 2 plus 0.2 pi r. And then I'm just going to set that to equal 0. And now to make it easier to solve, I'm going to turn it into negative 40 over r squared plus 0.2 pi r and set it to equal 0. And because I've done that, I can multiply everything by r squared to get rid of the r squared fraction and turn it into negative 40 plus 0.2 pi r cubed equals 0. Then I can add 40 to both sides to turn it into 0.2 pi r cubed equals 40. Then I can divide both sides by 0.2 pi. So r cubed equals 40 over 0.2 pi. And therefore, r equals the cube root of 40 over 0.2 pi. So then we can work out r. So we can put that into a calculator. And we get that r is approximately equal to 3.99 centimeters. So now that we have that, let's use the second derivative to see if it actually minimizes the cost. So the second derivative of the cost would be 80 r to the power of negative 3 plus 0.2 pi. Then if we plug our value for radius into that, 80 times 3.99 to the power of negative 3 plus 0.2 pi, you get about 1.89. And because that's a positive number, that means it's a minimum. So cost is minimized when the radius equals 3.99 centimeters. And now we can plug that into the volume formula to find the height. So 1000 equals pi r squared h. That means that h equals 1000 over pi r squared, which we actually already found earlier. But that means that h equals 1000 over pi times 3.99 squared, which is about 20 centimeters. So to minimize the cost, the radius would need to be 3.99 centimeters, and the height would need to be 20. And that's how you do optimization using calculus.